Alright, in this video we give a proof of L'Hopital's rule, and along the way we also prove a generalization of the mean value theorem that is called Cauchy's mean value theorem. Okay, let's start. So we first prove Cauchy's mean value theorem. This is a generalized version of the mean value theorem. Mean value theorem, and that is the following. Assume we have two functions f of x and g of x that are continuous on the closed interval between a and b, and also differentiable on an open interval between a and b. And we also assume that for all x in the open interval, g prime of x is non-zero. Okay, then this theorem states that there exists some c in the interval between a and b such that we have f prime of c over g prime of c is equal to f of b minus f of a divided by g of b minus g of a. Okay, so this is, this looks like the mean value theorem, but the difference is the denominator here. Previously, we had f of c is equal to f of b minus f of a divided by b minus a. But here it's different, and we have extra function g. And actually, if we assume that g of x is just x, okay, then g prime of x is just 1. So this becomes 1. And g of b minus g of a becomes b minus a. So indeed, this includes the usual mean value theorem. In other words, the usual mean value theorem is just a special case of Cauchy's mean value theorem. Okay, so let's prove this. First of all, we apply the usual mean value theorem to the function g because it satisfies the conditions for the mean value theorem. It is continuous between a and b, closed interval, and differentiable between a and b in open interval. So that means there exists, by the mean value theorem, there exists some d between a and b such that g prime of d is equal to g of b minus g of a over b minus a. Okay, and g, and this is not 0 by assumption. Okay, it's non-zero by assumption. Assumption means we assume this. So in the open interval between a and b, g prime is always non-zero. So that means this is non-zero, therefore g of b minus g of a is also non-zero. So that means we can define the following function without a problem. Let's define a new function h of x as, let's see, f of x minus f of b minus f of a over g of b minus g of a times g of x. Now let's calculate the values of this function at a and b. Okay, so h, by the way, this is just a constant, and it's a linear combination of g and f and g. So, h of x is continuous between a and b, including a and b, and also differentiable between a and b on open interval. Anyway, so let's calculate the value of h of a. So that is f a minus fb minus fa over gb minus ga times ga. Okay, so fa gb minus fa ga and minus fbga plus faga over gb minus ga. And this faga are cancelled. And we have fagb minus fbga and gb minus ga. And do the same thing for b. And if you do the same calculation, similar calculation, you actually get this is equal to the same value. So that is this. Okay, so we can apply Rolle's theorem. So by Rolle's, remember, theorem? So it's a special case of mean value theorem, but since the endpoints have the same value, there exists some constant c between a and b such that the derivative of h, the differential coefficient of h at c is equal to 0. But if we apply the definition of this h, the derivative of h prime means this is equal to f prime of c minus f of b minus f of a over g of b minus g of a times g prime of c. This should be equal to 0. Now, let's divide both sides by g prime and arrange the terms. Then we get, so f prime of c over g prime of c is equal to this thing. So fb minus f a over gp minus ga. And we are done. All right, so let's move on to proving L'Hopital's rule for the most basic case. So let us restate the theorem again. F and g are functions that are differentiable on this open interval between a and b. And we assume three conditions. Limit of f of x as x goes to a from the right is equal to limit of g of x as x approaches a from the right. They are both 0. And 2, for all x in the interval, g prime of x is non-zero. And 3, the limit of f prime of x over g prime of x as x goes to a from the right exists. Then we have this limit f of x over g of x as x goes to a from the right is equal to the limit of f prime of x over g prime of x as x goes to a from the right. So this is the theorem. And so, these two functions are only required to be differentiable on this interval. So we don't care their values at exact x equal to a or b. We only care about the limit here. So we can just assume or set f of a is equal to 0, and which is also equal to g of a. Okay, so we can set this for convenience in the following. Okay, so if we define the values of f and g at x equal to a as this, then from the first condition here, the right limits are 0. So that means f and g are continuous at x equal to a, right? So that means these functions are continuous in the semi-open or closed interval between a and b, including a. And since these functions are differentiable on this open interval, that means they are continuous on that open interval also. So that means for any x in this interval, f and g are continuous on between a and x, closed interval between a and x. And from the second condition here, for all t in this interval, a and x, g prime of t is non-zero. Okay, now we can apply Cauchy's mean value theorem. So that means, okay, by Cauchy's mean value theorem, there exists some c. That depends on x, by the way, between a and x, such that f prime of cx over g prime of cx is equal to f of x minus f of a over g of x minus g of a. But we define the values at a is 0, so this is actually equal to f of x over g of x. And now, if we move x to a from the right, that implies c of x also converges to a from the right. And this limit of f prime of cx over g prime of cx as x goes to a from the right. So this limit exists according to the condition 3. Okay, so this is fine. But this is equal to this. So limit f or going to a from the right, f of x over g of x. And this exists, so therefore this exists, and we are done. Okay, next we consider the case where f of x diverges to plus minus infinity, and so does g of x as x goes to a from the right. Okay, so first of all, let's define a constant L as the limit of this x goes to a from the right and f prime of x over g prime of x. So this is guaranteed to exist. So this is a finite constant L. Okay, so what this means is that if x is close enough to a, then this value becomes arbitrarily close to L. So in terms of epsilon delta argument, we can say that for any epsilon that is positive, there exists some delta, let's say delta 1 in this case, delta such that if x is between, since we are considering only the right limit here, between a and a plus delta 1 implies the difference between f prime of x and divided by g prime of x minus L is less than epsilon. And also from this condition, g diverges to plus or minus infinity, we can say that if x is close enough to a, let's say delta 2 in this case, then the absolute value of g of x is greater than, it can be any positive number, but let's say 1 is greater. It's always possible to make the absolute value of g of x greater than 1 if x is close enough to a. Okay, next let delta prime be the smaller of this delta 1 or delta 2. Delta 1 or delta 2. And let's define a constant d as a plus delta prime. And again, we apply Cauchy's mean value theorem. So by Cauchy's mean value theorem, for any x in the interval between a and d, there exists some constant cx that is between x and d, such that f prime of cx over g prime of cx is equal to f of d minus f of x and g of d minus g of x. Okay, let's modify this a little bit. Let's divide both numerator and denominator by g of x. So it's, since x is close to a, close enough to a, so x is between a and d, so it's less than d, so that means g of x is always greater than 1, right? And so let's multiply both numerator and denominator by -1 and divide everything by g of x, and we have f of x over g of x minus f of d over g of x over 1 minus g of d minus g of x. Okay, now let's multiply both sides by this. Okay, so we have, let's see, 1 minus g of d over g of x times f prime of cx and g prime of cx, and f of x over g of x minus f of d over g of x. Let's expand this, and we have f prime cx over g prime of cx equals to f of x over g of x. And so this times this moves to the right hand side, and let's factorize a little bit. This one, f of d over g of x minus f prime of cx over this one, g prime of cx times g of d over g of x. Okay, now let's put this as r of x. And since we're assuming that this g of x diverges to positive or negative infinity. So as x goes to a from the right, then that means, all these are constants, right? This is constant, this is constant, everything is constant except for g of x here. So g of x diverges to positive or negative infinity. That means this r of x, this term, converges to 0 because g of x is in the denominator. So let's subtract L from both sides and move this r of x to the other side, and we have this. So f of x over g of x minus L. We want to show that this function f over g converges to L, right? So now we have this f prime of x over g prime of x. No, it's not x, it's c of x actually. Cx and cx minus L plus r of x. Right? Now use the triangle formula, a triangle inequality. F prime cx over g prime of cx minus L plus absolute value of this. Okay. Now this converges to 0 and this converges to 0. That means, this is less than some arbitrarily small positive number. That is, let's say, epsilon. As we have introduced here, epsilon, this is less than this, and if r of x is if it converges to 0, then it can be arbitrarily small, that is less than epsilon. So we have this. That means this is less than some arbitrarily small positive number, and that means, after all, we have this thing converges to L as x goes to a from the right, and we are done. Now finally, we want to consider the case we take the limit where x goes to infinity rather than to a constant, either from right or left. But in this case, so in this case, f of x converges to 0. Let's assume converges, g of x also converges to 0. But in this case, if we just make a substitution, x equals to 1 over t, or t equals to 1 over x. Okay, so if x goes to infinity, then t goes to 0, and we can consider this composite function. Instead of f of x, we can consider f of 1 over t and g of 1 over t. Okay, so this is a new function of t. And then we can apply the other version, the previous version of L'Hopital's rule. And we are done, almost. And I'll skip the details. And if you want to see the details, see my lecture notes. All right, that's all for this video. See you later.